Tonight, we're going to sit with the strangest force in the universe, a force you have never felt, a force that is, in this very moment, pulling every galaxy you cannot see away from every galaxy you can. Most people assume the term dark energy is settled, that physicists know what it is, even if the public does not. They don't. Nobody does. But here's what most people don't realize. After 27 years of study, after Nobel Prizes, telescopes the size of buildings, and theories more elegant than the things they describe, the most powerful force in the universe still has no real name. Dark energy is a confession of ignorance, dressed as a label. And by the end of tonight, you're going to understand three things. Why the galaxies are drifting apart faster than the equations predicted. Why every candidate physics has offered for what's doing. The polling has, quietly, failed. And what it might mean to live in a universe whose dominant ingredient remains, after a quarter century, still without a name. If that sounds worth sitting with tonight, like and subscribe, and then settle in. We begin now. It started, as many things in modern science do, with a single graph that refused to behave. The year was 1997. The place, a workstation at the Lawrence Berkeley National Laboratory, on a hill above the San Francisco Bay. The man at the workstation was Saul Perlmutter. He led a project called the Supernova Cosmology Project, and he had been staring at the same plot for hours. Before we go further, we should pause on what was on that screen. The plot was simple. On one axis, the redshift of a distant exploding star, how far it was. On the other axis, its apparent brightness, how far its light had traveled. 42 of these explosions sat on the graph, each one a star that had died billions of years ago, each one a landmark in time, used to measure the shape of cosmic expansion. The shape was wrong. The stars were too faint. Faint in a supernova survey means far. Far in cosmology means the universe was, in the past, smaller than the equations had predicted. Smaller in the past means the universe must have been expanding more slowly back then. And more slowly back then means, today, it must be expanding faster. The universe, we had been told, was not supposed to do this. It was supposed to slow down, like a ball thrown upward, losing energy, eventually drifting back together. It was not slowing down, it was speeding up. Perlmutter checked the calibration. He checked the redshifts. He checked the dust correction, the small adjustment for light dimmed by gas and grit between us and the stars. He checked all of these things 3 or 4 times. The graph did not move. 2,500 miles away on the other side of the country, a second team was reaching the same conclusion. That team was led by Brian Schmidt, an Australian astronomer at Mount Stromlo Observatory. His postdoc, a young man named Adam Rees, was at Harvard. Together with their collaborators, they were called the High-Z Supernova Search Team. They had been racing Perlmutter for several years. They had been hoping their data would say something elegant, that the universe, as everyone assumed, was slowly losing energy to gravity and would, in time, fold back on itself. It was not folding back on itself. It was opening outward, faster, every billion years. Rees was 28 years old that autumn. He would later say that when the numbers first came in, he sat at his desk for a long time, telling no one. He assumed it was a bug. He assumed it was a calibration error. He assumed, almost as a reflex, that he had done something wrong. He had not done something wrong. By spring 1998, Both teams knew. Neither wanted to publish first. Neither, in their quieter moments, wanted to publish at all. Publishing meant standing in front of the entire community of cosmologists and saying something close to absurd, that the dominant ingredient of reality was a thing nobody had ever seen, or named, or theorized correctly, that 2/3 of the universe was missing from the model we worked with, and had been missing for as long as a model existed. From where we sit tonight, the discovery looks settled. It was not. The Nobel Prize would come in 2011, shared between Perlmutter, Schmidt, and Rees. The certainty would come gradually. But in 1998, sitting in front of those quiet, stubborn graphs, none of the three of them wanted to be the one to break the news. The number underneath their discovery, the violation that broke 30 years of cosmology, is where we turn next. A number that, once you've heard it, you don't quite forget. Roughly 68% of the universe, measured by mass and energy together, is the thing doing the pulling. 68% of everything. Sit with that for a moment. 68% of the cosmos is something we cannot directly detect. We cannot put it in a jar. We cannot describe it, even now, with a working theory. We can only measure very precisely what it does, and then sit like Perlmutter and Schmidt and Rees sat in front of the consequences. The rest is the visible rest, the stars, the planets, the galaxies, the dust between them, the gas inside them, the world you can touch. You, the chair, the floor under the chair, every atom of every breath you have ever taken. All of it accounts for roughly 5% of what is. 5%. The remaining 27% is another kind of darkness, called dark matter, which holds galaxies together, but does not, in itself, do the pulling. We will come back to it, and the largest piece, the largest by a long way, does not yet have a real name. The thing we have been calling dark energy is, by mass and by influence, the universe. Everything you can see, and everything you cannot see but can imagine, is the trim around it. The mountain ranges, the oceans, the sky, the sun, the other suns, the other galaxies, the rounding error. But to understand how anyone became confident of a number like 68%, we have to go back to the supernova themselves, to the strange, lucky fact that the universe has been kind enough to leave us standard candles to measure it by. In 1998, two independent groups of astronomers, working in direct competition with each other, published almost the same impossible conclusion within months. Neither group believed what they had found. To understand why, we should walk through how science of this kind actually gets done. The work was, at heart, statistical. You take a large set of distant supernova. You measure their redshifts. You measure their apparent brightness. You then fit a curve to the data, and the curve tells you the geometry of the universe across the time the light has been traveling. The standard expectation before 1998 was that the curve would tilt one specific way. The expansion of the universe, started by the Big Bang, was supposed to be slowing down. Gravity, pulling on all the mass inside the universe, was supposed to be winning. Cosmologists had a single number to capture this. They called it Q0, the deceleration parameter. The expected value was a small positive number. Positive meant the universe was decelerating, slowing, eventually perhaps drifting back together. That was, as far as anyone in the field was concerned, the only possible answer the data could give us. When Perlmutter's team and Schmidt's team fit their curves, Q0 came in negative. A negative deceleration parameter is not, in everyday language, a deceleration at all. It is an acceleration. The universe was not, as we had assumed, slowing down under gravity. The universe was, somehow, fighting gravity and winning. Adam Rees, working at Harvard that autumn, was the one who first saw the negative number written out on his own screen. He was 28 years old. The screen belonged to an early Pentium machine, sitting on a desk in a small office. The number that came up was the chi-squared, a statistical measure of how well a model fits a data set. It was telling him that the model everyone had been using did not fit the data, and that the model that did fit the data was the one nobody had wanted to use. Rees later said, in interviews, that his first reaction was to assume he had made a coding error. He stayed at his desk through the night, then through the next day, looking for it. There was no coding error. The high Z sample contained 42 Type 1a supernovae, explosions whose distances the team had measured to better precision than any previous catalog. 42, we should note, was not a huge number, but 42 was enough to put the statistics, when properly analyzed, beyond the threshold cosmologists call 3 sigma. The probability of getting the result by chance, by simple noise in the data, was less than 1 part in 1,000. 1 part in 1,000 is not, in physics, what we call certainty. Certainty is more like 1 part in 3.5 million, what the field calls 5 sigma. But 1 part in 1,000 is far past the line where you have to begin taking the results seriously. And Schmidt's team, running an independent analysis on a different data set, reached the same conclusion at roughly the same confidence. 2 teams, 2 methods, 2 answers that were the same answer. And the answer was that the dominant force in the universe on the largest scales was something that pushed. By the end of 1998, both teams had published. Both had pushed past their own hesitation, and both watched the cosmology community, over the following months, work through the same checks they had already done: the calibration, the redshifts, any quiet error that might rescue the old model. None was found. The lectures the 3 would give 13 years later, when the Nobel Prize finally came, were by Nobel standards unusually quiet. Each spoke in their own way about the strangeness of celebrating a discovery they had not wanted to make. To know why those 42 distant supernovae were the ones that could tell us this, we have to step back from the discovery itself. We have to understand what a Type 1a supernova actually is, and why, of all the explosions in the universe, this one detonates at almost exactly the same brightness every single time. There's one kind of explosion in the universe that always releases, almost without exception, the same amount of light. And because it always releases the same amount of light, it will tell you very precisely how far away it is. That property is so useful it has a name. Astronomers call it a standard candle. The story of how we found that candle begins in 1930 on a steamship crossing the Indian Ocean. Subrahmanyan Chandrasekhar was 19 years old. He was traveling from Madras in what is now southern India to England, where he had earned a scholarship to Cambridge. The crossing took weeks. He had very little to do, so he spent much of the journey doing what 19-year-old physicists apparently do. He worked. Specifically, he was trying to understand how a dying star reaches its end, A star spends most of its life in a kind of standoff. Gravity pulls inward. The heat of fusion pushes outward. The two forces balance for billions of years, and the star simply burns. But fusion eventually runs out of fuel. When it does, gravity wins. The star collapses. Stock footage cannot follow a star to its end, but the math can. For stars like our Sun, the collapse produces a white dwarf, a sphere of compressed matter roughly the size of Earth, held up not by fusion, but by electron pressure. It is a quieter ending, dense, hot, gradually fading, unstable, or so we assumed at the time. Chandrasekhar, working in a notebook on the rolling deck of that ship, found that the stability had a limit. The limit was this: if a white dwarf accumulates too much mass, electron pressure can no longer hold gravity back. The dwarf collapses again, and the collapse, almost instantly, triggers a detonation so powerful it briefly outshines the entire galaxy that contains it. The mass at which this happens is roughly 1.4 times the mass of our Sun. We call it the Chandrasekhar limit, in his honor. When he submitted the calculation to the Royal Astronomical Society 2 years later, the physicist Arthur Eddington publicly rejected it. Eddington was one of the most celebrated scientists in England. He had observed the bending of starlight during the 1919 eclipse that had made Einstein famous. And he was, on this particular question, wrong. Chandrasekhar spent years unable to get the result accepted. It took more than 50 years for the Nobel Committee to agree. The prize finally came in 1983. The limit, and what it means for us today, is at the heart of how we know the universe is accelerating. Here's the mechanism: a white dwarf sitting near a companion star, a binary pair, two stars in a slow mutual orbit, can steal gas from its partner. The white dwarf grows heavier, slowly, over millions of years. When its mass crosses the Chandrasekhar limit, it detonates. And because the detonation always starts from almost exactly the same mass, it always releases almost exactly the same energy. It is, when you sit with it, a strange kind of clock. A white dwarf in a binary system, growing imperceptibly heavier for 1 million years. Invisible until the moment it isn't. And then briefly, the brightest thing in its galaxy. Same energy, same peak brightness. Every time. That uniformity is the standard candle, an explosion that always burns at a known brightness, scattered across the universe at varying distances, is a ruler. You measure how bright the explosion appears from here, the apparent brightness, and compare it to the known brightness. The difference tells you how far the light has traveled, with precision. That is what Perlmutter's team and Schmidt's team were doing with their 42 supernovae. They were not simply observing explosions. They were measuring the geometry of the universe, one detonating white dwarf at a time. And what the geometry told them, reluctantly, finally, was that the universe was not the shape anyone had expected, not the shape we had worked with for 3/4 of a century. But distance, in cosmology, is never the whole story. And this is something we keep having to remember. While the supernovae measured distance, another kind of measurement had been quietly building for decades. One about motion, not position. And the moment those two measurements were set against each other, the universe stopped being a backdrop and became a process. One that had been going on for a very long time before anyone thought to measure it. In 1929, an astronomer at Mount Wilson Observatory in California published a small graph that quietly dismantled one of the oldest assumptions in science, the assumption that the universe was standing still. The astronomer was Edwin Hubble. The graph was 11 data points. It should not have been enough to change everything. It was. Hubble had spent years doing painstaking work, measuring the distances to faint smudges of light that some astronomers thought were nearby gas clouds and others thought were something far stranger. Entire systems of stars, as large as our own galaxy, impossibly far away. By 1924, Hubble had settled the question. The smudges were galaxies. The universe was vastly larger than anyone had seriously believed. That was already unsettling enough. What came next was worse. Working on cold California nights with the 100-inch Hooker telescope above him, at the time the largest telescope on Earth, Hubble compared two measurements. The first was the redshift of each galaxy, how much the light from that galaxy had stretched toward the red end of the spectrum on its way to us, a signature of motion away from us, the same principle that drops the pitch of a passing siren. The second was the distance to each galaxy, measured using the same kind of standard candle we just described, variable stars called Cepheid Squonq, whose brightness pulses in a predictable rhythm. He plotted the two measurements against each other, and a line appeared. The line said something simple and enormous. The farther a galaxy sits from us, the faster it moves away. Every galaxy was receding, and the recession was not random. It was proportional. Double the distance, double the speed. It was a relationship so clean it looked like a law. We now call it Hubble's law. The number that describes it, the rate at which recession speed grows with distance, is the Hubble constant. Measured locally, it comes in at roughly 70 miles per second for every 3.25 million light years you travel outward. That is a number worth sitting with. Every 3.25 million light years of additional distance adds roughly 70 miles per second to the speed at which a galaxy moves away from us. The universe was not standing still. It was expanding. Every galaxy was moving away from every other galaxy, not through space, but with space, the way raisins in a rising loaf of bread move apart, not because they are swimming through dough, but because the dough itself is growing. Space, it turned out, was not an empty stage. Space was something that could stretch. Hubble was careful about what he claimed. He published the data and let others draw the conclusion. The conclusion, drawn most clearly by the Belgian priest and physicist Georges Lemaitre several years earlier from Einstein's own equations, was that the expansion implied a beginning. Run the expansion backward, and everything converges. Once, there was a single point. Then there wasn't. Hubble's data was the observational confirmation of what the math had already whispered. And here's the thing about an expanding universe that becomes important for everything we will discuss tonight. If the universe is expanding now, and if the expansion is governed by gravity and by whatever else is inside the universe, then the history of that expansion is a record of the forces that shaped it. Measure how the expansion rate has changed over time, whether it has been slowing or holding steady, or, as Perlmutter and Schmidt and Rees found in 1998, accelerating. And you have measured, indirectly, everything that the universe contains. That is why the supernova surveys mattered so much. They were not just measuring distance. They were reading the universe's history of forces. And the history said that something was pushing. That was already strange enough. But if the universe is expanding now, then once, long ago, everything must have been closer. And if everything was closer, then everything was hotter. And if everything was hotter, then there must be a moment near the very beginning where the heat itself left a faint, ancient signal still spread across the sky, cooling and dimming for billions of years until it became almost too quiet to hear. Almost. Somewhere in the galaxy, a molecular cloud drifts slowly, wide enough to swallow several light years in each direction, cold and dark and thick with dust. The interior holds a silence that has no equivalent on Earth, made of cold and distance and the absence of anything that could carry sound. The dust inside is older than the solar system, silica and carbon and iron grains held in a gas that sits just above absolute cold. The cloud drifts, and the motion is too slow for any lifetime to register, too gradual even for instruments to read as movement. But somewhere in the deepest part of this cold, a slow gathering is beginning, invisible from outside and barely visible from within, not yet warm enough to glow, just a region where the gas is slightly denser and gravity is drawing the nearest threads of dust and hydrogen slowly inward. The drawing in is gentle and without urgency, the way very large things always seem to move slowly even when they are not. The cloud does not rush, and the warmth at its center grows by slow degrees, and the dark around it holds it gently. The galaxy turns slowly overhead, ancient and steady and indifferent to the small becoming happening deep inside this cold. Something is being made here, slowly and without announcement, in the cold and silence at the center of this patient dark. It will take a very long time, and the surrounding space holds it, and nothing about the silence suggests any urgency at all. The equation that describes dark energy was written down in 1917 by a man who would, 12 years later, declare it the greatest mistake of his life. The man was Albert Einstein. The mistake was a single Greek letter. By 1915, Einstein had finished general relativity, the theory that replaced Newton's gravity with a description of space-time itself, bending under the influence of mass and energy. The equations were among the most elegant in the history of physics. They were also, when applied to the universe as a whole, deeply inconvenient. They predicted a universe in motion, either expanding or contracting, never still. This was a problem. In 1915, the universe was assumed to be static, eternal, unchanging, the same yesterday as today as a billion years from now. Every philosopher and physicist of the era held this assumption so quietly and so completely that it barely registered as an assumption at all. It was simply the nature of things. The universe was permanent. It did not move. Einstein trusted his equations. He also trusted the assumption. And so, in 1917, he did what anyone might do when their mathematics disagrees with their certainties. He adjusted the mathematics. He added a term, a single Greek letter placed on the left side of the field equations, lambda, the cosmological constant, a kind of repulsion built into the fabric of space itself, a pressure pushing outward at exactly the rate needed to counterbalance gravity and hold the universe in place. The universe, with lambda in the equations, could be static, eternal, safe. It was, Einstein later said, the most natural thing to add. Lambda was dimensionally consistent. It did not break anything. It simply sat there, doing its quiet work, keeping the cosmos still. Then Edwin Hubble published his 11 data points. By 1929, the universe was no longer static. It was expanding. The galaxies were moving. Space itself was stretching. The assumption that had made lambda necessary evaporated, and with it, lambda's reason for existing. Einstein removed the term from his equations. In a conversation with the physicist George Gamow some years later, he called it the biggest blunder of his career. He had allowed his philosophical preference for a still universe to corrupt his equations, and the equations had been right all along. Lambda was gone. The universe was expanding. And for the next 69 years, that was the end of the story. Then, in 1998, Perlmutter and Schmidt and Rees published their supernova surveys. The universe was not only expanding, it was accelerating. And when theorists sat down to describe an accelerating expansion mathematically, to find the simplest equation that could accommodate the data, they found that the simplest equation was the one Einstein had written in 1917, the one with lambda in it. Lambda was back, not as a term holding the universe still, as a term driving the universe apart. The cosmological constant Einstein had added to preserve the static cosmos had, in a different form, returned to describe its opposite. Not a gentle equilibrium, but an ongoing, accelerating dissolution. The same letter, an entirely different role. We call it lambda CDM now, lambda cold dark matter, the standard model of cosmology. Lambda sits in the equations as a constant energy density associated with empty space, uniform across the universe, unchanging with time. It is the most economical description of what the supernova surveys observed, and it fits the data remarkably well. It just does not explain anything. Lambda is a number, a very specific number, measured to several decimal places by the best telescopes we have. But a number is not an explanation. A number tells you how large the effect is. It does not tell you where the effect comes from, what it is made of, or why it has the value it has, rather than any other value. The question that immediately followed the return of lambda, the question that has not been answered in 27 years since, is the question of what lambda actually represents. What property of space? What field? What substance, if it is a substance at all, could produce a repulsion so precisely tuned and so uniformly distributed that it looks, from every direction and at every scale, exactly like a constant? That is the question we turn to next. And the first candidate answer is, by a wide margin, the most embarrassing prediction in the history of physics. The most natural candidate for what lambda might be is the energy of empty space itself. This sounds strange. Empty space, by definition, should have no energy. But quantum mechanics disagrees, and it disagrees loudly. In quantum field theory, empty space is not empty. It seethes with activity. Fields permeate all of space. The electromagnetic field, the electron field, the quark fields, a dozen others. And even in their lowest possible state, their ground state, these fields are not at zero energy. They fluctuate. Virtual particles flicker in and out of existence, borrowing energy from the vacuum for intervals so short that no instrument can directly detect them. The vacuum, it turns out, has a baseline energy, a hum. Wolfgang Pauli was among the first physicists to take this seriously in the 1930s. He calculated the zero-point energy of the quantum vacuum and noted, with characteristic dryness, that if his estimate were correct, the radius of the universe would not even reach to the moon. The energy density was impossibly high. He set the calculation aside as unphysical and moved on. Most physicists did the same. The vacuum energy was treated as a bookkeeping artifact, real in the mathematics, ignorable in practice. That changed in 1998. Because if lambda is real, and if lambda represents a constant energy density of empty space, then the vacuum energy cannot simply be ignored. It has to match. And when physicists calculated how large the vacuum energy should be, using the best available quantum field theory, and compared it to how large lambda actually is, they found a disagreement that is difficult to describe without losing the sense of how catastrophic it is. The predicted vacuum energy is larger than the observed value of lambda by a factor of 10 raised to the power of 120, one followed by 120 zeros. There's no other prediction in all of physics that is wrong by this margin. It is not a small error. It is not a factor of 2 or 10 or a million. It is the largest discrepancy between theory and observation ever recorded, by an amount so vast that the usual language of scientific error simply stops working. Physicists call it the vacuum catastrophe, or the cosmological constant problem, and it has been sitting at the center of theoretical physics for 27 years without a resolution. The number itself is worth sitting with for a moment. 120 orders of magnitude. If the theoretical prediction were a distance, and the observed value were a single atom, the prediction would be larger than the observable universe, by a factor that makes the observable universe look like the atom. That is how wrong it is. And here's what makes it stranger still. The vacuum energy does not just fail to match lambda. It fails in a very specific way. The theoretical value is enormous, enough, if real, to have torn space apart in the first instant after the Big Bang, long before galaxies or stars or atoms could form. The observed value of lambda is tiny, almost nothing compared to the energy scales of particle physics, but just large enough to produce the slow acceleration we see today. Why is lambda so small? Not zero. Zero would be easy. Zero might mean a symmetry, a cancellation, a reason, but not quite zero. Why does it have this particular tiny value, so far below what quantum field theory predicts, and yet not zero? This is what physicists call the fine-tuning problem, and it is the second layer of the cosmological constant problem, sitting under the first. Steven Weinberg, who won the Nobel Prize in Physics in 1979, argued in 1987 that the only way to understand the smallness of lambda might be anthropic, that in a universe where lambda were much larger, structure would never have formed, and there would be no one to measure it. It was a controversial argument then. It remains controversial now. It is also, so far, the closest thing to an explanation that anyone has published. The vacuum catastrophe remains open, and the candidate it was supposed to confirm, vacuum energy as the source of lambda, remains not confirmed, not refuted, and not understood. The next candidate is more elegant. It is also, so far, equally unsupported. Take everything you can see in the night sky, every star in every galaxy, every planet, every cloud of gas and dust, and weigh it all. Add it up. You will have accounted for roughly 5% of the universe. The other 95% is something else entirely. We have touched on this already, briefly, but it is worth staying with, because the story of dark energy cannot be told without understanding that it sits inside a larger mystery, one that has two parts, and that both parts arrived as surprises. If this is the kind of night that makes you want to stay close to these questions, like and subscribe. It helps us keep making them. Now back to the 95%. The first part of the mystery arrived in the 1970s in the data of an astronomer named Vera Rubin. Rubin was measuring the rotation of galaxies, specifically how fast stars at different distances from a galaxy's center were orbiting. In a system governed by visible matter alone, the physics is straightforward. Stars near the center, where most of the mass is concentrated, should orbit fastest. Stars at the outer edges, far from the bulk of the mass, should orbit more slowly, the way the outer planets of our solar system orbit more slowly than the inner ones. They did not. The outer stars of galaxy after galaxy were orbiting just as fast as the inner stars, in some cases faster than they had any right to. The visible matter could not produce enough gravity to hold them in those orbits. By all the physics Rubin and her collaborator Kent Ford could apply, the outer stars should have been flung outward long ago. The galaxies should have come apart. They had not come apart. They were intact and spinning steadily, and the only explanation was that a large quantity of invisible mass was distributed throughout each galaxy, not concentrated at the center like the visible stars, but spread in a wide halo, providing the gravitational scaffolding the stars needed. Rubin published these results quietly and carefully, against the resistance of a field that was slow to take them seriously. She was right. The invisible mass is what we now call dark matter, matter that does not emit or absorb light, does not interact electromagnetically, and makes itself known only through gravity. It is the scaffolding inside which every galaxy sits. The second part of the mystery arrived in 1998. We have already described it, the accelerating expansion, lambda, the thing we cannot name. Together, these two discoveries produce the modern inventory of the cosmos. Roughly 5% ordinary matter, atoms, protons, neutrons, the stuff of stars and planets, and the bodies sitting in the dark right now. Roughly 27% dark matter, invisible, gravitationally active, holding the architecture of the universe in place. And roughly 68% dark energy, the unnamed, undetected, theoretically unresolved force pulling every unbound galaxy away from every other. 5, 27, 68. We evolved to perceive the 5%. We built our science, our languages, our philosophies, our religions on the assumption that what we could see was what there was. And it turns out that what we could see is the rounding error, the trim around the edge, the caption at the bottom of a picture whose main subject we have not yet been able to read. That is not a criticism of the human enterprise. It is, in a way, its strangest achievement, that we managed, using only the 5% we can see, to deduce the existence and the rough proportions of the other 95. That Vera Rubin, sitting with data about spinning galaxies in the 1970s, could conclude there was something vast and invisible holding them together. That Perlmutter and Schmidt and Riess, measuring the brightness of distant explosions, could conclude there was something vast and invisible pushing everything apart. We know the proportions. We do not know what fills them. And yet the proportions themselves are known because of something very specific. A faint warmth left over from the universe's earliest moments, spread across the entire sky, carrying in its tiny temperature variations a precise record of everything the early universe contained. That warmth is the oldest light there is, and it is the subject we turn to next. It arrives from every direction at once, so evenly that it feels less like a signal and more like a temperature. A warmth so faint and so ancient that no human sense could register it without instruments, and yet so uniform that it fills the entire sky without gap or shadow. This is not a place. It is a time, still arriving. The light set out when the universe was very young and very hot, and the atoms of that early universe were too dense and too energetic to let any light pass through them. And then slowly, the universe cooled, and the density thinned, and the light that had been trapped inside that hot fog was suddenly free to travel, streaming outward in all directions at once, and it has been traveling ever since. It moves through the space between galaxies, and through the space between walls, and through the space between the molecules of whatever you are resting against tonight. And it carries within its faint and even warmth a record of the moment the universe first became transparent to its own light. The warmth is everywhere, and it is old beyond any image the mind can hold, and it settles across the whole sky like something that was always there, patient and smooth and soft, the way the air in a room holds a temperature long after the source of the warmth has gone quiet. It arrives, and it arrives, and it arrives, and the sky holds it gently in every direction, and nothing about the darkness suggests it will ever stop. If dark energy is not a constant, if it changes over time, grows stronger or weaker as the universe ages, then it is not lambda at all. It is a field, something that fills space the way a temperature fills a room, with a value that can vary, and a history, and perhaps an end. That possibility has a name. It was proposed in 1998, the same year the supernova surveys were published, by two physicists who were thinking about dark energy at the same moment the data was making dark energy impossible to ignore. Robert Caldwell and Paul Steinhardt were working at the University of Pennsylvania. Steinhardt had already spent years thinking about the early universe and the physics of fields that could drive rapid expansion. When the supernova results arrived, he and Caldwell turned those ideas toward the current epoch and proposed something specific, that the accelerating expansion might be driven not by a fixed constant, but by a dynamical field, one that evolved over cosmic time, whose energy density changed as the universe grew older. They needed a name for it. They reached back to Aristotle. In classical philosophy, the universe was made of 4 elements: earth, water, fire, air. But the heavens were different from the earth. The celestial spheres, the stars and their motions, could not be made of earthly matter, which was heavy and impermanent. So Aristotle proposed a 5th element, filling the space above the moon, weightless and eternal and carrying the stars in their orbits. He called it the ether, or sometimes, in later translations, the quintessence, the 5th thing, the stuff of the sky. Caldwell and Steinhardt borrowed the name. Their quintessence was not Aristotle's. It was a quantum field, governed by equations from modern physics, but the spirit was the same, something filling space, something belonging to the heavens, something different in kind from ordinary matter. Here's what makes quintessence a different prediction from lambda. Lambda is a number, fixed, unchanging, the same at every point in the universe and at every moment in cosmic time. quintessence has an equation of state, a number physicists label W, that describes the relationship between its pressure and its energy density. For a true cosmological constant, W equals exactly -1. For a quintessence field, W is close to -1, but not exactly, and it shifts as the universe evolves. That shift is, in principle, measurable. If quintessence is correct, then the accelerating expansion we measure today is not the same as the accelerating expansion that was happening 5 billion years ago, or that will be happening 5 billion years from now. The expansion is a phase, one chapter in a longer story, whose ending the field itself encodes. Dark energy in this picture is not eternal. It had a beginning somewhere in the early history of the universe, and it will have an end when the field eventually settles or decays into something else. This changes the feel of the whole problem. Lambda is not a story. Lambda is a number sitting in an equation, doing what it does, forever. Quintessence is a process, and a process can be understood in a way that a fixed constant, stubbornly and silently present, resists being understood. Steinhardt spent years developing the theory, refining the predictions, proposing specific quintessence models with specific equations of state that could, in principle, be distinguished from lambda by precise enough measurements. Other theorists joined the effort. The field grew. Tracker fields, thawing fields, freezing fields, each a variation on the same core idea, each predicting a slightly different W at a slightly different time. And then the measurements came in, -1, every time. Year after year, survey after survey, the equation of state of dark energy landed on -1. Exactly what lambda predicts, exactly what quintessence, in most of its forms, predicts only as a special case. The measurements were not precise enough to rule quintessence out, but they were not finding any evidence of variation. Elegance is not evidence, and a theory that predicts something measurable is only useful if the measurement eventually returns something other than the same answer every time. Until very recently, it did not. And then quietly, one instrument began to suggest otherwise. There is another possibility, one that almost no working cosmologist takes seriously as a complete solution, but that refuses year after year to fully disappear. The possibility that the problem is not dark energy or dark matter or the universe. The possibility that the problem is the theory of gravity itself. It is worth taking seriously for a moment, not because the evidence strongly favors it, but because it illustrates something important, that when a theory fails to explain observations, there are always two places to look: the data and the framework used to interpret the data. The challenge to the standard gravitational framework began not with dark energy, but with dark matter, and it began with a single physicist working quietly against the current of his field. Mordechai Milgram was at the Weizmann Institute of Science in Israel in 1983 when he proposed a modification to Newton's law of gravity. The idea was simple in outline. At high accelerations, the kind experienced by objects near the centers of galaxies or in our own solar system, gravity works exactly as Newton and Einstein described. But at very low accelerations, below a certain threshold, Milgram proposed that gravity behaves differently. It falls off more slowly with distance than the standard equations predict. The motivation was Vera Rubin's galaxy rotation data. If gravity at low accelerations was stronger than the standard equation said, then the outer stars of galaxies would orbit faster than standard physics predicted, exactly what the observation showed. No dark matter required, no invisible scaffolding, just a modified law. Milgram's framework became known as modified Newtonian dynamics, or MIONE. It was received with polite skepticism by most of the physics community, and with active hostility by some. For the next 2 decades, it sat at the margins, producing occasional fits to rotation curve data that were genuinely impressive, failing at larger scales in ways that were genuinely problematic, and refusing to go away entirely. Jacob Bekenstein extended MOND into a relativistic theory in 2004, calling it tensor vector scalar gravity, or TVIS, an attempt to embed Milgram's modification into a framework compatible with general relativity and capable, in principle, of addressing the full range of cosmological observations. It addressed some of them. It struggled with others. The test that most physicists consider decisive came in 2006. The bullet cluster is the name given to the aftermath of a collision between 2 large clusters of galaxies. The clusters pass through each other, and in doing so, the hot gas, which makes up most of the ordinary matter in galaxy clusters, was slowed by electromagnetic interactions and lagged behind. The galaxies themselves, being effectively collisionless, passed straight through. When astronomers mapped the gravitational lensing of background light around the bullet cluster, the bending of light that reveals where the mass actually sits, they found that the mass was not where the hot gas was. The mass was where the galaxies were, and beyond them, in a region containing very little visible matter at all. The mass was invisible, and it had passed through the collision without slowing. Modified gravity, in its standard forms, predicts that the gravitational mass should follow the ordinary matter. In the bullet cluster, it did not. Dark matter, a particle or particles that interact only gravitationally, passing through each other and through ordinary matter, fits the observation naturally. MOND and its extensions do not fit it without significant additional assumptions. For most cosmologists, the bullet cluster closed the argument. Dark matter is real. The modifications to gravity, whatever their merits at galaxy scales, are not the whole story. For a small, persistent minority of physicists, the argument is not closed. Modified gravity theories continue to be developed and refined, and some of their proponents argue that the full picture remains unresolved. The debate is quieter than it was. It has not ended. What has not ended for anyone is a different and more recent problem, one that sits inside the standard model rather than outside it, and that has been quietly worsening for over a decade. 2 different ways of measuring how fast the universe is expanding today give 2 different answers. The gap between them is growing, and it should not exist at all. The universe is expanding. On that, every measurement agrees. The question is, how fast? And the answer depends entirely on how you ask it. There are 2 ways to measure the current expansion rate, and they are both well established, both carefully checked, and both right. The trouble is that they do not give the same answer. The first method works outward from the nearby universe. You start with stars whose distances you can measure directly. Cepheid variables, the same pulsing stars Hubble used in 1929, you calibrate those against type 1a supernovae. You use the supernovae to measure distances to galaxies billions of light years away. You watch how fast those galaxies are receding. And from all of that, you derive a number, the Hubble constant, the rate at which recession speed grows with distance. Adam Rees has led the most precise version of this measurement for over a decade, using the Hubble Space Telescope and then the James Webb Space Telescope to push the calibration to better than 1% precision. The number his team arrives at, consistently, is roughly 73 kilometers per second per megaparsec. In more immediate terms, roughly 165,000 miles per hour for every 3.25 million light years of distance. The second method works backward from the early universe. You take the detailed map of the cosmic microwave background, the faint warmth we described earlier, the oldest light in the universe, and you fit the standard cosmological model to its temperature variations. The model predicts a Hubble constant. That prediction, from the Planck Satellite Collaboration's most precise analysis, comes in at roughly 67 kilometers per second per megaparsec. 73, 67. The gap between them is about 9%. That may not sound large. In cosmology, at this level of precision, it is enormous. Both measurements have been checked, rechecked, audited by independent teams, reproduced with different instruments and different techniques. The systematic errors have been hunted for years. None large enough to close the gap has been found. The disagreement now sits at what statisticians call 5 sigma, the threshold beyond which the probability of it arising from chance or measurement error drops below 1 in 3.5 million. The field has a name for it: the Hubble tension. Wendy Friedman at the University of Chicago has led an independent effort to measure the local Hubble constant using a different kind of standard candle, the tip of the red giant branch, a feature of stellar evolution that can be used as a distance marker without relying on Cepheid variables. Her team's measurements sit between the two numbers, closer to 69 or 70, which some physicists read as evidence that the tension may partly be a calibration problem. Others read the same result differently. The debate is ongoing and unresolved. What is not debated is this: something in the standard model is either wrong or incomplete. Either the local measurements have a systematic error that nobody has yet identified, which is possible, or the early universe measurements have a systematic error that nobody has yet identified, which is also possible, or there is a piece of physics between the early universe and now that the standard model does not contain. That third possibility is the interesting one, because if the Hubble tension is real, if it reflects genuine missing physics rather than measurement error, then the history of the universe's expansion is not as smooth and uninterrupted as lambda CDM assumes. Something happened, or is happening, that the model does not account for. A new particle species in the early universe, a brief episode of early dark energy, a modification to the way dark energy or dark matter behaved at particular epochs. None of these solutions have been confirmed. Several have been proposed, tested against other data, and found to solve the Hubble tension while breaking something else. The problem resists clean resolution, and still, the distance between everything widened, gently, as it has for billions of years. What widened it, and at what rate, and whether that rate has always been what we measure today. These remain among the most actively contested questions in cosmology, and they connect directly to the most recent data from an instrument in the Arizona desert that has begun to suggest something unexpected about the force at the center of all of it. The surface is cold in a way that settles into the body slowly, the kind of cold that does not announce itself but simply becomes the temperature of everything: the rock underfoot, and the dark overhead, and the air that is not quite air, too thin to breathe and too still to feel as wind. There's no sun here. There has never been a sun here. This world drifts between the stars, belonging to none of them, following a path so long and so gradual that the stars themselves have shifted their positions in the sky since it began. The horizon is close and flat and perfectly dark, and above it, the galaxy stretches across the whole overhead sky. A soft, pale band of light so faint, it seems less like something seen and more like something sensed. A presence, a warmth that is not warmth, a company that asks nothing and offers nothing, and simply is. The ice plane catches the galaxy's light at a low angle, and the surface holds a faint luminescence, blue-gray and smooth, interrupted here and there by the slow upwelling of old rock that has been rising for longer than the Earth has existed. There is no sound. There has been no sound here for a very long time, and the silence is not empty, but full of cold and stillness, and the sense of a place that has been waiting patiently for nothing in particular, and is entirely at rest, and does not mind the dark at all. In April of 2024, a collaboration of hundreds of scientists released the first major results from an instrument that had spent 3 years mapping the universe's largest structures with greater precision than any previous survey. The instrument was the Dark Energy Spectroscopic Instrument, mounted on the Mile 4-meter telescope at Kitt Peak National Observatory in the Sonoran Desert of Arizona. DESI was built for one purpose: to measure how dark energy has behaved across cosmic time. The way it does this is elegant in principle and staggering in scale. Sound waves rippled through the hot plasma of the early universe, the same plasma that eventually released the cosmic microwave background. Those waves left a faint imprint in the distribution of matter, a preferred spacing between galaxies, a subtle clustering at a particular scale, preserved in the large-scale structure of the universe like a fossil in stone. By measuring that scale at different distances, and therefore different epochs, DESI can trace how the expansion rate has changed over billions of years. The collaboration's first-year results covered roughly 6 million galaxies and quasars spanning 11 billion years of cosmic history. The team's analysis compared those results against the predictions of lambda CDM, the standard model with its fixed, eternal cosmological constant. The fit was not perfect. The data showed a mild but consistent preference for dark energy that was not constant, not lambda, something that had been stronger in the past and was weakening over time, or something whose equation of state, that number tau we discussed earlier, was drifting away from -1 as the universe aged. The signal was not overwhelming. At roughly 2 to 3 sigma confidence across the first-year dataset, it sat below the threshold physicists call a discovery. It was a hint, a suggestion, the kind of result that makes a field lean forward in its chair. Will Percival at the University of Waterloo, one of the senior figures in the collaboration, described the result carefully. noting the statistical significance, acknowledging the caveats, and making clear that confirmation would require the full 5-year data set and independent verification from other surveys. This is how careful science sounds. It does not shout. The second-year results, released in 2025, slightly strengthened the signal. Not enough to declare the cosmological constant dead, enough to keep the question open in a way it had not been open for several years. If the DESI result holds, and that remains a large and genuine if, then lambda is not the answer. Dark energy is not a fixed property of space. It is something that changes, something with a history, something that, in principle, could be understood in the way that things with histories can be understood, by asking where it came from, how it evolved, and where it is going. That would be the most significant revision to the standard model of cosmology since the supernova surveys of 1998. It would reopen every candidate theory that constant measurements had seemed to close. Quintessence would move from the margins toward the center. The vacuum catastrophe would need to be reframed. The Hubble tension would gain a new possible context. It would also mean that the universe we live in is stranger than even the strange picture we have been building tonight. Not a cosmos coasting on a fixed dark energy toward a distant heat death, but something more dynamic. A universe whose dominant ingredient is in motion, whose future is less settled than we thought, whose ending, if there is an ending, depends on the behavior of something we have not yet managed to name. The DESI collaboration will release its full 5-year results within the next few years. Other surveys, the Euclid Space Telescope, the Vera Rubin Observatory's Legacy Survey of Space and Time, will add independent measurements. The picture will sharpen. For now, the hint sits in the data, unconfirmed, unrefuted, quietly suggesting that the force with no name may also have no fixed nature. And still, the distance between everything widened, gently, as it has for billions of years. There's a future scenario, mathematically permitted by the current data, in which the very last thing in the universe to come apart, after the galaxy clusters, after the galaxies, after the solar systems, after the planets, after the molecules, is the atom. And the moment it happens, space itself ceases to exist in any meaningful sense, and the universe ends not with a slow fade, but with a sudden, total dissolution. This scenario has a name. It is called the Big Rip. Robert Caldwell, the same physicist at Dartmouth who, with Paul Steinhardt, had proposed quintessence in 1998, returned to the equations in 2003 and asked a different question. Not what if W is close to -1, but slightly above it? What if W is below it? For a cosmological constant, W equals -1 exactly. For quintessence, W is greater than -1, but the equations do not forbid a value smaller than -1. Mathematically, nothing stops it. Physically, a field with W below -1 is deeply strange. It would violate certain energy conditions that physicists usually assume hold in nature. But it is not impossible, and the data at the time could not rule it out. Caldwell called this field phantom dark energy, and he worked out what the universe would look like if it were real. In a phantom dark energy universe, the energy density of dark energy does not stay constant as space expands. It grows. The more space there is, the stronger the dark energy becomes. And as the dark energy strengthens, the expansion accelerates further, which creates more space, which strengthens the dark energy further still. The process is self-reinforcing. Runaway. And at its end is what Caldwell named the Big Rip. The sequence unfolds over cosmic time in a specific order, determined by the binding energies of the structures being torn apart. Galaxy clusters, the largest gravitationally bound objects in the universe, go first, their galaxies drifting apart as the expansion overwhelms gravity at that scale. Then individual galaxies are disrupted, then solar systems, then planets, then, in the very final moments, in a compression of time that Caldwell's calculations placed at fractions of a second before the end, the dark energy tears apart atoms themselves, electrons stripped from nuclei split, the strong force overwhelmed, and the universe reaches a state of infinite expansion density in finite time. The Big Rip, in the most extreme phantom energy models, would arrive somewhere between 20 and 100 billion years from now, depending on exactly how far below -1W turns out to be. Most cosmologists do not think this will happen. The current data does not require W below -1. The central value of most measurements sits at -1 or slightly above it, firmly in lambda, or mild quintessence territory. The phantom regime is at the edge of the error bars, not at the center. But the edge of the error bars is not ruled out. And this is worth holding for a moment. The data we have, the best data in the history of cosmology, gathered by satellites and telescopes and supernova surveys of extraordinary precision, does not exclude a future in which every structure in the universe, down to the proton, is eventually pulled apart by the force we cannot name. The shape of the universe's ending is still, in this sense, an open question. The next decade of measurements, DESY's full results, the Euclid satellite, the Vera Rubin Observatory, will push the error bars on W inward. If W stays at -1, the Big Rip recedes from possibility. If W drifts below it, the scenario becomes harder to dismiss. For now, it sits in the data as a permitted future, not required, not excluded. The kind of possibility that physics tolerates because the equations allow it, and the measurements have not yet closed the door. Before we follow that thread further into the future, though, we should pause on a quieter question, one that does not require phantom energy or runaway expansion, but simply asks whether the whole picture might look different depending on where, in the universe, we happen to be standing. The simplest explanation for the supernova data, simpler than dark energy, simpler than a modified cosmological constant, simpler than any new field or phantom force, is that the universe is not accelerating at all, that we are sitting in an unusual place, and the unusual place is making the universe look different from how it actually is. This is the local void hypothesis, and it deserves a fair hearing, not because the evidence strongly supports it, but because it represents the kind of explanation that scientists are obligated to consider before invoking new physics. The possibility that the observation is an artifact of the observer's position. The argument runs like this: the universe, on the very largest scales, is assumed to be roughly the same in every direction and at every location. This assumption has a name: the cosmological principle. It is built into every standard model of cosmology. It is well supported by surveys of the large-scale structure of the universe. The distribution of galaxies across billions of light years shows a foam-like pattern of filaments and voids that is, statistically, consistent with homogeneity and isotropy when averaged over large enough scales. But on smaller scales, scales of hundreds of millions of light years, the universe is not smooth. There are dense regions and underdense regions, superclusters and voids. And if the Earth and its surrounding neighborhood happen to sit inside a particularly large and deep underdensity, a bubble of space with significantly less matter than the cosmic average, then the galaxies at the edge of that bubble would appear to be receding faster than expected, even if the universe as a whole were not accelerating. The local void hypothesis had serious advocates in the years following the supernova discoveries. Timothy Clifton and Pedro Ferreira at Oxford published detailed analyses of what such a void would need to look like to reproduce the observed acceleration. The numbers required a bubble roughly 300 million light-years across, with a matter density somewhere between 20 and 40% below the cosmic mean. Subsequent surveys looked for it. The surveys found something. The region around our galaxy does appear to sit in a mild underdensity, what some astronomers call the KBC void, named after Keenan, Barger, and Cowie, who characterized it in 2013. The void is real. The question is whether it is large enough and deep enough to explain the full acceleration signal. The answer, from the most careful analyses, is that it is not. The KBC void is shallower and smaller than the local void hypothesis requires. It might account for a portion of the Hubble tension, the gap between local and early universe expansion rate measurements. But it cannot, on its own, explain away the accelerating expansion entirely. The cosmological principle, meanwhile, has held up well against the best available data. The universe is not perfectly smooth, but it is smooth enough, on large enough scales, that sitting in a local underdensity cannot substitute for dark energy as a complete explanation. There's also the question of probability. The cosmological principle predicts that large, deep voids of the kind the hypothesis requires should be extremely rare. If we happen to be sitting in the center of one by chance, that would itself require an explanation, one that, in some formulations, is as uncomfortable as the dark energy it was meant to replace. For these reasons, the local void hypothesis is not the current consensus position. Most cosmologists treat the KBC void as a genuine but modest feature of the local universe, worth accounting for in precise measurements of the Hubble constant, but not as an alternative to dark energy. The acceleration, as best we can tell, is real. The force behind it is real, and the force is everywhere. Not a feature of our neighborhood, but a property of space itself, present at every point, in every direction, at every scale above the gravitational binding energy of the structures it has not yet managed to pull apart. We are not in a special place. The universe is simply doing this everywhere, and the thing driving it remains, in every direction we look, without a name that means anything beyond the data that demanded it. There are places in the universe where nothing is close, where the nearest galaxy sits so far away that its light arrives as a suggestion rather than a source, a faint smear at the very edge of what any instrument could detect. And the space between here and there is simply space, cold and dark and unbroken in every direction. This is one of those places. The emptiness here is not the emptiness of a quiet room or a desert at night, or even the space between the Earth and the Moon. It is a different quality of empty altogether, a vast and settled absence so complete that it stops feeling like the absence of something and starts feeling like a presence of its own, the presence of stillness, of distance, of a cold so deep and so even that it has become the temperature of the place rather than the absence of heat. Nothing moves here with any urgency. Nothing moves here at all on any time scale a life could register. The dark holds itself in every direction without edge or boundary, and the faint light of distant galaxy clusters drifts at the very margins of the visible, steady and remote and soft. There's no sound. There's no wind. There's a cold that is simply the temperature of space, and a dark that is simply the color of everything, and a silence so wide and so settled and so old that resting inside it feels somehow like being held. When the conservative explanations have been tested and found insufficient, when lambda fits the data but cannot be explained, when quintessence is elegant but unconfirmed, when modified gravity handles some observations but fails others, the speculative explanations start to get a hearing, not because the evidence demands them, but because the evidence has not yet closed them out, and because the problem is serious enough that no reasonable possibility should be dismissed unexamined. Some of these ideas rewrite the nature of empty space. Some rewrite gravity from its foundations. One suggests that the universe itself is a kind of projection, that what we experience as three-dimensional space is the surface of something deeper, and that the forces we measure are shadows of processes happening on a boundary we cannot directly observe. Erik Verlinde is a theoretical physicist at the University of Amsterdam who, in 2010, published a paper proposing that gravity is not a fundamental force at all. In Verlinde's framework, gravity is emergent. It arises from the statistical behavior of information encoded on the surfaces of regions of space, the way thermodynamic properties like temperature and pressure emerge from the collective behavior of molecules without being properties of any individual molecule. The idea draws on a deep connection between gravity, thermodynamics, and information theory that physicists have been exploring since the 1970s, when Stephen Hawking and Jacob Bekenstein showed that black holes have entropy and temperature, properties that suggested gravity and thermodynamics were more deeply linked than anyone had realized. Verlinde extended this connection. In his framework, dark matter is not a particle. It is a modification to the way entropy behaves in regions of space that have been influenced by the mass of ordinary matter, a kind of elastic response of the underlying information structure of space to the presence of baryonic matter. And dark energy in this picture is similarly an emergent consequence of the entropy of de Sitter space, the particular geometry of an accelerating universe. The framework makes some predictions that agree with observations. It reproduces certain features of galaxy rotation curves without invoking dark matter particles. It provides a physical picture of lambda that does not require a fine-tuned vacuum energy. It is genuinely interesting. It has not so far produced a confirmed prediction that the standard model cannot also match. Verlinde's work sits alongside a family of related ideas: holographic dark energy, in which the dark energy density is related to the information content of the cosmic horizon; brain world cosmologies, in which our universe is a four-dimensional surface embedded in a higher dimensional space, and the apparent acceleration is a consequence of gravity leaking into the extra dimensions, and various formulations of entropic or emergent gravity in which both dark matter and dark energy dissolve on close enough examination into properties of information rather than properties of stuff. Each of these frameworks has serious physicists working on it. Each has had moments of genuine promise, and each has, so far, encountered observations it could not cleanly accommodate, or failed to produce predictions sufficiently precise and distinctive to be tested definitively. This is the graveyard that theoretical cosmology has become, not in a discouraging sense, but in the sense that it is full of beautiful ideas that are not yet dead and not yet alive, ideas that are mathematically coherent, physically motivated, and observationally underdetermined, ideas that are waiting, sometimes patiently, and sometimes less so, for the data that will either confirm them or close them out permanently. The DESI results, when complete, will constrain the equation of state of dark energy to a precision that will test some of these frameworks directly. The Euclid satellite is mapping the large-scale structure of the universe with a resolution that will push others. The next generation of gravitational wave observatories will probe the behavior of spacetime at scales where emergent gravity theories make distinctive predictions. The data is coming. The ideas are waiting. And after a quarter century of work, after Nobel Prizes and satellite missions and surveys of millions of galaxies, the cosmologist sits with a strange and honest set of certainties, confident that something is happening, confident to within a few percent how much of it there is, and confident of almost nothing about what it actually is. The conversation turns now toward the future the unnamed force is making. If dark energy is constant, if lambda holds its value and the expansion continues as it has been continuing, then the future of the universe has already been written, not in detail, but in broad outline. And the outline is strange in a way that only becomes clear when you extend the timeline far enough. The galaxies we can see tonight belong, mostly, to the observable universe, the sphere of space from which light has had time to reach us since the beginning. That sphere has an edge, and beyond the edge, space exists, but its light cannot reach us, because the universe expanded too fast for the light to cover the distance. That edge is not a wall. It is a horizon, and like all horizons, it moves as we move through time. In an accelerating universe, the horizon does not simply sit still while we observe it. It contracts, in a sense, not in physical size, but in what it admits. The accelerating expansion means that galaxies far enough away are receding from us faster than light can travel between us. Once a galaxy crosses that threshold, its light will never reach us again. It has not disappeared. It has simply become permanently unreachable. The window has closed. Lawrence Krauss at Arizona State University and Robert Scherer at Vanderbilt published a paper in 2007 with a title that captures the situation precisely: The Return of a Static Universe and the End of Cosmology. They calculated what the observable universe would look like to astronomers living roughly 100 billion years from now. Assuming lambda holds, the answer was stark. In approximately 150 billion years, every galaxy outside our local group, the cluster of roughly 80 galaxies, including the Milky Way and Andromeda, that are gravitationally bound to one another, will have receded beyond the cosmological event horizon. their light will still be traveling. It will simply never arrive. Those galaxies will be gone from the observable universe as completely as if they had never existed. The Milky Way and Andromeda will have merged by then, a process already underway. The two galaxies moving toward each other at roughly 70 miles per second, expected to begin their collision in about 4.5 billion years. What emerges from that merger, astronomers sometimes call it Milkomeda, will be the only galaxy in the future observer's sky. One galaxy surrounded by void in a universe that appears, from every measurement available to those future observers, to be static and eternal. The cosmic microwave background will have stretched by then into wavelengths so long that no plausible instrument could detect it. The evidence of the Big Bang will be gone. The evidence of the expansion will be gone. The evidence of the other galaxies will be gone. Those future astronomers working with the best physics and the best telescopes available to them will conclude, correctly given their evidence, that the universe contains one galaxy and nothing else, and has always contained one galaxy and nothing else. They will be wrong, and they will have no way of knowing it. We live in the only epoch in the history of the universe when the evidence for the expansion is available. The light from distant galaxies still reaches us. The cosmic microwave background is still detectable. The recession velocities of thousands of galaxies can still be measured. The full picture is still, barely, visible. The unnamed force is the thing closing that window. It is accelerating the recession of every galaxy beyond our local group, driving them toward the horizon and eventually past it, erasing one by one the very observations that allowed us to discover it. Dark energy will outlast the evidence for dark energy. The expansion will outlast the observability of the expansion. That we found it when we did. That Perlmutter and Schmidt and Rees published their supernova surveys in 1998, and not 100 billion years later, when there would have been nothing left to observe, is not something the universe planned. It is an accident of timing. A window that happens to be open during the few billion years when beings capable of looking through it exist to look. The term dark energy was coined in 1998 by a physicist named Michael Turner at the University of Chicago. He meant it as a placeholder, a working label, something to write in the papers while the real name was being worked out. The real name, Turner assumed, would arrive once the theory arrived. Once someone understood what the thing actually was, and could name it accordingly, the way physicists had named the electron once they understood what the electron was. The theory has not arrived. The placeholder is still here. Turner has described the moment of naming in various interviews over the years. It was at a meeting in the months after the supernova results were published, and the community needed something to call the new thing. Dark matter was already in use for the invisible gravitational scaffolding of galaxies. Whatever was driving the acceleration was different. Not clustering, not cold, not associated with structure, but it was similarly invisible, similarly unnamed, similarly pervasive. Turner reached for a parallel. Dark matter, dark energy. The symmetry was clean, and the phrase was memorable, and it filled the gap that the data had opened. He did not expect the phrase to still be in use 27 years later. It is worth sitting with what the two words actually mean, because they mean less than they imply. The word dark in dark energy does not carry its everyday meaning. It does not mean black. It does not mean shadowy. or hidden or threatening. In physics, dark is a technical term for something that does not interact with electromagnetic radiation, does not emit light, does not absorb light, does not reflect it. It is dark in the precise sense that it is invisible to any instrument that works by collecting photons, which is to say, every optical telescope, every radio telescope, every gamma-ray observatory ever built. Dark energy does not show up in any of them, not because it is too faint, but because it does not interact with light at all. The word energy is, if anything, even more approximate. Energy in physics has a specific meaning: the capacity to do work, a conserved quantity, something that flows and transforms and obeys precise thermodynamic laws. Whether dark energy is energy in this sense is genuinely unclear. It might be a property of space-time geometry rather than a form of energy in the traditional sense. It might be a field with an energy density. It might be something for which the concept of energy, as physicists currently define it, does not cleanly apply. We do not know. We use the word because we need something to write in the equations, and energy density is how lambda enters the mathematics, and so energy is what we call it. Dark energy. Two words borrowed from adjacent concepts, joined together to point at something that has so far resisted every attempt to understand it well enough to name it properly. This is not, historically, unusual. Atom meant indivisible, and atoms turned out to be divisible. Electron was a word borrowed from the Greek for amber, before anyone knew what an electron actually was. Quark was lifted from a line in James Joyce. The names of fundamental things are almost always wrong at first. Provisional handles grabbed in the dark, correct enough to work with, replaced when understanding deepens. The difference with dark energy is the time scale. The electron was named in 1894, and its charge and mass were measured within a decade. Quarks were named in 1964 and confirmed experimentally within 10 years. Dark energy was named in 1998, and we are, 27 years later, still working with the same placeholder, while the theory it was meant to hold space for has not materialized. The placeholder has outlasted the careers of the physicists who proposed it. It has outlasted entire generations of instruments. It appears in every cosmology textbook, every press release, every educational video about the universe. It has become, through repetition and familiarity, something that sounds like a real name. It is not a real name. It is a confession, written in two words, that the dominant ingredient of the universe remains unknown, which raises very gently the strangest possibility we have yet considered tonight, that the reason no name has stuck is not that we have not found the right one, but that the thing we are trying to name is not, in any familiar sense, a thing at all. We have followed a long road tonight, and it is worth pausing here to take stock of where it has led us. We began with two teams of astronomers who did not want to believe their own data. We followed the data backward through the history of the idea, through Hubble's expanding universe, through Einstein's discarded constant, through Chandrasekhar's limit, and the white dwarfs that became cosmic rulers. We watched the Standard Model absorb the shock of the supernova results and incorporate them, producing a picture of the universe in which 68% of everything is something no one can explain. We examined every candidate that physics has offered for what that something might be. The vacuum energy of quantum field theory, wrong by 120 orders of magnitude. quintessence, elegant, unconfirmed, waiting on measurements that so far return the same unhelpful answer. Modified gravity, impressive at galaxy scales, unable to account for the full picture. The local void, real but too shallow, too small, insufficient. Holographic emergence, entropic gravity, phantom energy, brain worlds, mathematically interesting, observationally underdetermined, beautiful ideas in a graveyard. None of them has landed cleanly. And yet something emerges from the wreckage of all these attempts that is itself a kind of finding. Every theory in this list, every candidate from the most conservative to the most speculative, agrees on something. They agree that the universe is doing something the original equations did not anticipate. They agree that the missing piece is large and pervasive and old. They agree that whatever it is, it fills space uniformly, operates at every scale above a certain threshold, and produces an effect that, measured to several decimal places across billions of years of cosmic history, looks precisely like a constant. The disagreement is about what lies beneath that constant. The convergence is about the fact of it. That convergence is not nothing. It is, in its way, the most important thing we know about dark energy, that it is so stubbornly consistent, so uniform, so relentlessly present in every survey and every measurement and every calibrated instrument we have pointed at it, that even our failures to explain it are all failures of the same particular kind. Something is there, something large and quiet and old, something the universe has been doing since long before there was anyone to notice. And still, the distance between everything widened, gently, as it has for billions of years. There's a particular kind of humility that comes not from being small, but from being confused. Not the humility of standing beneath a sky full of stars and feeling the weight of scale. That humility is familiar and in its own way comfortable. The smallness that resolves into wonder. This is a different kind. The humility of having built the most precise instruments in the history of science, pointed them at the largest structures in the universe, gathered data across billions of light years and billions of years, and arrived at a description of reality in which the dominant ingredient remains, after all that effort, genuinely unknown. We are not small in the face of the universe tonight. We are confused in the face of it. And that confusion is, in its own quiet way, one of the most honest things about us. Consider what it means to live in this particular moment. The universe is roughly 13.5 billion years old. The evidence for its expansion, the galaxies, the cosmic microwave background, the large-scale structure, is still visible to us, still measurable, still legible. 100 billion years from now, as we described earlier, that evidence will have dissolved. The galaxies will be gone past the horizon. The background warmth will have stretched beyond detection. The expansion will have made itself invisible by completing itself. We are here in the window. The narrow band of cosmic time when the universe is old enough to have produced beings capable of asking questions about it, and young enough that the answers are still available to be found. That coincidence is not guaranteed by any law of physics. It is simply where we happen to be. And still, the distance between everything widened, gently, as it has for billions of years. What we have done with our position in that window is remarkable, even measured against the scale of what we do not know. We have determined that the universe began. We have measured when. We have mapped the large-scale structure of the cosmos across billions of light years. We have detected the faint afterglow of the universe's first light. We have weighed the contents of the universe to within a few percent and found that 95% of it is invisible to us. We have discovered that the expansion is accelerating, that something is driving it, and that the something is real and large and present everywhere. We have not, in all of that, managed to say what the something is. This is not a failure, or rather, it is the particular kind of failure that represents the frontier, the edge of what the current generation of tools and theories can reach. Every generation in the history of science has had a frontier of this kind, a place where the questions run ahead of the answers, and the honest response is to build better instruments, propose better theories, and wait for the data that will eventually force the picture to resolve. The data is being gathered now. DESI is mapping galaxies. Euclid is measuring shapes. The Vera Rubin Observatory is surveying the southern sky. The results will arrive in the coming years and decade, and they will either confirm the Standard Model's description of a constant dark energy, or they will begin to show the cracks that point towards something deeper. Either outcome is extraordinary. A confirmed lambda tells us that the universe has a fixed, uniform property of empty space that nobody can derive from first principles, and that this property happens to have a value that allows galaxies and stars and planets and us to exist, and that no theory currently in existence explains why. An evolving dark energy tells us that the universe has a dynamical field filling all of space, with a history and perhaps an ending, and that we have been observing only one phase of its behavior, and that the full story is longer and stranger than the current picture suggests. Either way, the universe is telling us something. We are still learning to hear it clearly. And in the meantime, the something at the center of the mystery continues its quiet work. Patient, pervasive, unnamed, and the space between the galaxies continues to widen, and the night continues to deepen. And here we are, briefly, in the window. There's a place above the plane of the galaxy where the disk itself becomes visible, not as a band of light crossing the sky the way it appears from inside, but as a structure, a slow spiral seen from a great height, its arms trailing outward from a bright, dense center, the whole thing turning at a rate so gradual that a single human life would not be enough to see it move. From above, the scale of it changes everything. The stars that felt close from inside, the ones with names, the ones ancient civilizations built their calendars around. From here, they are indistinguishable from the other 400 billion stars turning in the disk below. The sun is somewhere in one of the outer arms. It is not findable from this distance. It is simply part of the light. And surrounding the disk, spread in a wide and nearly spherical halo that extends far beyond the visible spiral, are the globular clusters, dense, ancient collections of stars, some containing 100,000 suns each, orbiting the galaxy in long, slow paths that carry them out into the halo and back again over hundreds of millions of years. The clusters are old. Some of them formed when the universe was less than 1 billion years old. They have been orbiting ever since, patient and unchanged, while the galaxy below them built its spiral arms and filled them with younger stars, and watched some of those stars explode and scatter their elements outward for the next generation to use. The disk turns. The clusters orbit. The halo holds it all in a gravitational embrace that has been holding for longer than the Earth has existed, longer than the solar system, longer than anything on the surface of our world has been present to experience. And still, the distance between everything widened, gently, as it has for billions of years. From this height, the dark energy we have spent the night discussing is not visible as a thing. It has no surface, no color, no edge, but its work is visible in the space between this galaxy and the nearest other galaxy, in the space between this cluster of galaxies and the next, in the slow recession of every unbound structure from every other unbound structure. The spiral below is one of the things the expansion has not yet reached. It is bound to its neighbors by gravity, safe inside the local group, carried along as a unit by the larger flow, but internally coherent, internally patient, still turning at the same rate it has always turned. That rate is, by the standards of human experience, impossibly slow. The solar system takes a very long time to complete a single orbit around the galactic center. So long that in the entire history of complex life on Earth, it has not yet come all the way around. And yet from above, the motion is perceptible, not as speed, but as structure. The arms, the dust lanes, the star-forming regions glowing faintly at the edges, all of it the visible record of motion sustained over billions of years. The halo above and around the disk is darker. The globular clusters glow softly, each one a concentrated warmth of ancient light, spread across the halo in orbits that carry them out and back in rhythms, too long for any civilization to have observed from start to finish. They have been there since before the disk below had taken its current shape. They will be there, orbiting, long after the last star in the disk has cooled. The silence out here is different from the silence of a void. The void we visited earlier was empty, genuinely, completely empty. No light, no structure, nothing to register as presence. Up here in the galactic halo, there's presence. The presence of all that mass and all that light and all that accumulated time, arranged in a structure so large and so patient that the word patience stops being a metaphor and starts being a description. The disk turns. The clusters drift outward and return. The dark between the stars holds its temperature. The expansion continues at the very largest scales, far beyond the gravitational reach of this galaxy or its neighbors. And the unnamed force does its quiet work out there in the spaces between the superclusters, and none of it disturbs the stillness up here in the halo. Nothing is urgent. Nothing is rushing. The light from the old clusters falls slowly downward through the halo and through the disk and out the other side, and the galaxy receives it and does not notice. And the long, slow night of deep time continues, and the dark is soft, and everything that is here has been here for a very long time. We began tonight with a force that pulls, something vast and unnamed, working in the spaces between galaxies, widening every distance, moving every unbound thing slowly and irresistibly away from every other unbound thing. We framed it at the start as something strange and perhaps unsettling, a dominant ingredient without a name, a force that will eventually pull the observable universe into silence. But here, near the end of the night, the same force looks different. The unnamed thing is why the universe is mostly dark. It is why the night sky is quiet rather than filled from horizon to horizon with the blinding light of an infinite static cosmos. It is why there is distance between things and space for things to form and room for the slow, patient processes, stellar nurseries, collapsing clouds, 4 billion year sequences of chemistry that eventually produced, among everything else they produced, the capacity for anyone to lie in the dark and wonder about any of this at all. The force that has no name is also the force that made the quiet. The darkness it is pulling things into is the same darkness that holds you tonight. And still, the distance between everything widened, gently, as it has for billions of years. Whatever it is, constant or field, vacuum energy or something we have not yet imagined, a number in an equation or the shadow of a deeper truth, it has been doing this work since long before tonight, and it will be doing it long after. The galaxies will continue their slow recession. The halo will keep its long orbits. The old light will keep arriving from all directions. Whatever it is, it will still be doing its work in the morning. You can rest now. The cosmos will keep going without you, as it always has. If this night spent with the nameless force brought you a quiet moment, if the long, slow walk through what we know and what we don't has settled something, or opened something, or simply kept you company in the dark, we are glad you are here. There are more nights like this one. The same voice, the same unhurried pace, the same long, slow walk through the things that science has found, and the things it is still reaching for. If that sounds like the kind of company worth keeping, subscribe, and we will be here when you need it. Until next time, rest well. The universe is not going anywhere. The questions will still be there in the morning, patient as they have always been, and so will we.